Okay, solving problems with torques can be interesting. The idea is you need to identify your fulcrum and then identify your torques. So remember, if something is going to be in static equilibrium, our net torque is going to be equal to 0, which means that your counterclockwise equal your clockwise, and your net forces are going to equal 0, which means your up forces will equal your down forces, or your left forces will equal your right forces. So these are the basic ideas that we are going to be working with. So we need to identify the fulcrum. Okay? Here's our problem. We have a 1200 Newton beam. So that would be this guy right here. It has a weight, so that's already a force, of 1200 newtons. And it's 3.5 meters long, suspended by 2 vertical wires. So there's one wire and there's the other wire. A small but dense weight of 550 newtons, so that's already a weight, that's already a force, you don't have to do anything to it, is on the beam 2 meters from one end. So it looks like it's 2 meters from end B, as shown in the picture. And we're trying to find the tension in A and the tension in B. Okay? So we kind of have to do this in 2 problems. One of the things you want to do is think about, okay, if this guy is being pushed, where is it going to pivot? So if I push, if this guy here's pushing down, and let's say this wire wasn't here, because this wire's applying a force, correct? If this wire's pulling up, let's just talk about that wire. If that wire's pulling up, where is it going to pivot? It's going to pivot right there, right? And if this guy's pushing down, it'll pivot on that spot, and if that guy's pushing down, it'll pivot on that spot. Okay, so if we're going to find the tension in A, B is going to be our fulcrum. Okay, because if I pull up on A, can you see this beam here is going to come up, but it's going to kind of stay hooked here at position B. Okay, so treating B as our fulcrum. Okay, what torques do we have? Well, the tension in A is going to go up away from the beam, and remember, our torques are always going to go towards the fulcrum. So here's our force, and then it's going to go towards the fulcrum. So the torque in A, the torque from tension A is, follow it around the clock, is clockwise. All right, the 550 Newton little mass here, okay, it's going to push down, and it's going to go around towards the fulcrum. Down and towards the fulcrum. So if we follow that in a circle, so the torque from our weight then, from the 550 kilogram weight, is counterclockwise. All right, so far so good. Now the beam itself. The beam itself applies a torque. Okay, where is that torque being applied? Remember, the beam itself has a weight. Okay, and if A weren't here, so kind of pretend A is not there. If A weren't there, this would just flop down. Okay, so can you see it's a counterclockwise torque here? Counterclockwise torque. Where is that force being applied? The weight is applied at the center of mass. So the center of mass of this beam, okay, we're going to assume it is a perfectly uniform beam unless they tell us otherwise. So, and they won't tell us otherwise, probably. So the center of mass of this perfect beam would be in the perfect center of it. So it would be halfway through that 3.5 meters. And so halfway through 3.5 is the 1.75. So the torque from the beam, we'll just go ahead and call it the beam, is also counterclockwise. Remember, it's going to go down and towards the fulcrum. So it's also counterclockwise. So this is in static equilibrium. So the torque from A is clockwise, and that's going to equal our two counterclockwise torques added together. So far, so good? All right, so how is this going to look when we actually solve it? Remember, torque is the force times the distance. Okay, the lever arm. That R, remember, is our lever arm. So A, the lever arm, is this whole distance here. It's the distance from our fulcrum, and the length of that whole beam is 3.5 meters. So we're going to have the tension in A, and let's call it, instead of calling it T, because then you get it confused with torque, let's call it Ft in A times the distance, 3.5 meters, is equal to, okay, the 550 newtons, the force. Okay, remember, we didn't have to do anything to that because it's already in newtons. If it were in kilograms, we would have to take our kilograms and change them to newtons first, times its distance. Remember, it's 2 meters from B. See, it's 2 meters from B. So drawing these pictures out is very helpful, and labeling all your torques is very helpful. So times 2 plus the weight of the beam, 1,200, times its lever arm, the distance it is from B, which is 1.75 meters. And so now, thankfully, we have one unknown in our equation, and so we can solve for the force of tension in A, and we can get 914 newtons. Okay, so that's the tension in A. So we're halfway done. Halfway done, almost. Good to go? So that's the tension in A. Why didn't we take into account B? That is an awesome question. Why didn't we take into account B? How far is B from the fulcrum? B is actually on the fulcrum. So its distance, its lever arm is 0. So whenever you multiply any number times 0, this is not going to apply a torque at all. It's basically just pushing straight down. So we can be a little tricky. We can find the tension in B two different ways. We can be a little tricky. We're going to do it with the torques, and then I'm going to show you the other way we could do it. Okay, so when we were trying to find the tension in A, we used B as the fulcrum. Now we're going to make A the fulcrum. So it's going to pivot on A, because if we break B, this whole assembly is going to go flopping down, and it's going to stay attached here, and it's going to pivot on that spot right there. Okay, so A is going to be our fulcrum. So let's figure out what direction all of our torques are going to be. B is pulling up, and so we're going to go up and towards the fulcrum. So if you see that, that is going to be counterclockwise. Do you see that's going against the clock? So the torque from B is counterclockwise. The torque from the 550 is going to go down and towards the fulcrum. And so that's going to be, if we continue the circle around, you see that that's clockwise. So the torque from the 550 mass is going to be clockwise, and the torque from the weight of the beam itself, because even without this on it, the beam is going to flop down. The torque from B is also going to be down and towards the fulcrum, so it also is clockwise. Okay, so we have the same situation. The torque from B is going to equal the torque from our 550 plus the torque from the beam, or our counterclockwise is going to equal our two clockwise together. So the torque from B is the force of tension from B times how far is it from A. So it's 3.5 meters from A, equals the 550 Newton. Now, how far is that from our fulcrum? It's not 2 anymore. It's not 2. You might think it's 2, but we want this distance. We need this distance here. So this distance here from the mass to the fulcrum is now 1.5 meters. Because the whole beam itself, this whole beam is 3.5 meters, and this distance is 2 meters, so these two have to add up to the 3.5. That makes this 1.5. So the lever arm for the 550 now is 1.5 meters. It's a little bit different. Plus the 1,200 newtons of the beam. The beam hasn't changed its mass. And then remember, its center of mass was at the middle. Okay, it was being applied at the middle. So if this distance is 1.75, then this distance here is also 1.75 meters. And look, again, we only have one unknown, so the force of tension from B comes out to 836 newtons. So the force of tension in B was a little bit bigger than the force of tension in A. So let's see what we had here. Okay, so here's what we know. The force of tension in A was 914 newtons. The force of tension in B was 836 newtons. Okay? So we have those two up forces and these two down forces. Remember how we were talking about static equilibrium and our up forces needed to equal our down forces? Okay, so we have 914 newtons going up plus the 836 newtons going up, and that should equal our 550 newtons going down and our 1,200 newtons going down. And if this is a perfect world, this is 1750. This should add up to 1750. 914 plus 836. The proof is in the pudding. 1,750 newtons. Look at that. Look at that. Now here's, remember I said there were two ways we could do it. Here's what we already knew. We already knew this number and this number. And we had already calculated this number. So we could have used this idea here that our net force had to be 0 to find this number. We found it with the torques, but we confirmed it by saying all of our up forces equal all our down forces. And I'd rather you did it with the torques and then use this as confirmation that your answer is correct. But see how well that worked out? It's a perfect world. All right, so this is similar to what you're going to do in your lab, except for you're going to have normal forces, okay? Tension force, normal force, The only difference is it's applied by a surface instead of a string, but the idea is the same. So you're going to use one as the fulcrum to calculate the other, and then the other as the fulcrum to calculate the first. You'll see it more when we do the lab. Alrighty, there you go. Get to work on ye old practice problems. You can do it. Alright, see ya.